Which one?
3A.
3A, very good. So in 3A we have limit as x approaches 0 from the right, from sine x natural log x. Should I copy the b as well or not? Or we did b?
We did B.
Okay. I can still do it again if we need to, or we choose others. Okay, so first of all, I know that this approach is 0 and this approach is infinity or negative infinity. So this is the product type of indeterminate case, which is not as cumbersome as the power. This is not a difficult, normally not a difficult situation, the product. Okay, so since it's not 0 over 0, infinity over infinity, I have to try to change it into that. And I will. I will never bring down natural log. That will be a catastrophe. But I know that I can change that into cosecant. Because cosecant is 1 over sine. So if this is 1 over sine, I can flip it and I get the same thing. So now I'm hoping that this situation is infinity over infinity or 0 over 0. And it is. This is still infinity, and 1 over 0 is still infinity. Only now I can apply L'Hopital's rule, which I couldn't before. So this is limit as x approaches 0 from the right. So please do not forget to write the limit operator. Because without the limit operator, this is incorrect. So remember, the limit operator gets dropped at the very end when you're finished with the limit. Okay, so then the top prime is 1 over x. And the denominator prime, so remember cosecant prime is negative cosecant cotangent. Okay, negative cosecant x cotangent x. Now, let's take a look at this product before we proceed. So cosecant is 1 over sine. Cotangent is cosine x over sine x. So this whole thing could be replaced by cosine x over sine squared. Okay, I'm going to do that. So this is limit as x approaches 0 from the right, 1 over x at the top, negative cosine x over sine squared x. And then I divide. I have limit as x approaches 0, 1 over x times negative sine squared over cosine x. Now, when x approaches 0 from the right, cosine approaches 1. So that is not a problem. So this is limit as x approaches 0 from the right from, I can put the negative 1 in front or not, doesn't matter, sine squared x over x. And if you remember, we talked about this, negative sine x over x times sine x. It's a simple algebraic manipulation of the function. I change sine squared over x into sine over x and sine x, which is the same thing. But I know that this goes where? Yes, only when x approaches 0. Or 0 from one side, it doesn't matter. This approaches 1. And then I know that negative sine x would approach, yes. Indeed.
So you took
Yes.
cosine x over sine squared x and you flipped it?
Yeah, because I divide two fractions. So I copy the fraction from the top, and I multiply it by the multiplicative inverse of the denominator.
And the sign still stays the same.
Yes, sine squared, yes.
Uh-huh.
Yes. And cosine when x approaches 0, cosine is not a problem. I could have used L'Hopital's rule, but I didn't want to use L'Hopital's rule on the product. Although it's not a, we're going to get the same thing. So you can, from here, you don't have to do this if you don't want to. Just use L'Hopital's rule because it's 0 over 0. And you will get the same thing. Okay, other questions from me? Yes, please.
The last one, number 7.
Yes. That's a silly problem. It's a silly one. So we have f of x, which is L divided by 1 plus a e to negative x over b. And they're telling us that the maximum, the function increases at the maximum rate when y equals L over 2. So what does that mean? So let's talk about it for a moment. Exactly. When the second derivative is 0. When the second derivative is 0. So when we talk about increasing, decreasing, we're looking at the first derivative, right? So we will know when the function is increasing and decreasing. But the question now is not just when it's increasing or decreasing, but when it's increasing at the fastest rate. It's when the second derivative is 0. So the fastest rate is when the second derivative will be 0. So I have to go through the torture of finding the first and finding the second, and then I'll set it equal to 0, right? So, but if I do the antiderivative, then I'm going back to the function whose derivative is that, right? So we want to determine the first and the second. Okay, just making sure that I still have paid. Yes, I do. Okay, so f prime. Of course, I'm going to differentiate this. L times 1 plus a e to negative x over b to negative 1 prime. I'm not trying to avoid the quotient rule. I'm just trying to avoid an unnecessary quotient rule when the numerator doesn't have x in it. So when I differentiate, I bring down negative 1, so this is negative L times 1 plus a e to negative x over b raised to negative 2. Now careful what follows next. So I bring down negative 1, I subtract 1 from the power, but now I have to differentiate this. So 1 prime is 0, so times a times e to negative x over b times the inner function prime over, yes, yes. So negative 1 times that quantity to negative 2 times the inner function prime, which is a times e to negative x over b times the inner function prime, which is negative 1 over b. Is this clear? Yes? All steps? So now I'm going to take the negative L, the positive a, and the negative 1 over b in front. They're all constants. I don't care for them. I can wait patiently. So LA over b, and this is 1 plus a e to negative x over b raised to negative 2 times e to negative x over b. And yes, it starts being a little messy because now it's a product. It's a product of this function and this function. So I have to use the product rule when I find the second derivative. And I have to get two terms, right? Two sums. A sum of two products, right? Any questions so far? Any questions?
Oh, yeah.
Yes? No?
I was going to say, don't forget the negative, but the 2 negatives cancel out.
Yes. But don't trust me, please. So the second derivative now, LA divided by B. I differentiate the first one, negative 2 times 1 plus a e to negative x over b raised to negative 3 times a times e to negative x over b times negative 1 over b times e to negative x over b. Why are you making me do? Oh, no, I'm just kidding. Okay, so I bring negative 2 down, I subtract 1 from the power, I differentiate the inner, a times e to negative x over b times the inner function prime, negative 1 over b times the second function. Are we okay so far?
This is a good extra question.
plus, I copy the first function now, times the second one prime, e to negative x over b times negative 1 over b. Okay, what do you think we have to do next? Absolutely mandatory. Whatever, as much as possible, otherwise I can't do this. Right, so let me refresh your memory right here for a second. This is one term, and this is the second term. So we are looking for common factors. Obviously, e to negative x over b is in both. Obviously, negative 1 over b is in both. And also, this is in both. But the question is, which power do I pull out? Which is a negative 3. Very good. Very good. It must be negative 3. That's the lowest of the two. Okay. So then the second derivative is, maybe I should use, no, I'm kidding. LA over B. Okay, what is out? E to the negative x over b is out. I will put a negative in front and put b squared because negative 1 over b is also out. So this is gone, this is gone, this is gone, this is gone from both, of course. And also you said 1 plus a e to negative x over b to negative 3. So this is gone, but this one not entirely. So now please tell me what is left in brackets. So it is a negative 2, and it is an a, and it's this, correct? Okay, so I have negative 2a e to negative x over b plus. Yes, 1 plus a e to negative x over b. Excellent.
Did you come up with this question?
Say it again?
Did you come up with this question?
No, I will not take credit.
Because we took away,
Yes, we
Lower
took a
power.
yes.
H.
So we subtract from negative 2, we subtract negative 3, which is 1. Yes, perfect. So now this will go to the denominator, this will go to the denominator, then we have a negative that I will pull out and cancel that. So this is LA over B times, this goes to the denominator, this goes to the denominator. And this is a negative 1, so this is a e to negative x over b and minus 1. Yes, after all this effort, it simplifies nicely. And no, I did not come up with it. I wish I had. So when the second derivative is 0, what has to happen? So this, no, nothing cancels out. So for this to be 0, only this can be 0. The top. Nothing else. So then this implies a e to negative x over b minus 1 equals 0. From here, would you agree if I write a e to negative x over b equals 1? Would you agree with that? Okay, so then a e to negative x over b is 1, means this is 1. So the second derivative is 0 when the function is L over 2. So that means y equals L over 2. We just went back to the original function and then we replaced AE to negative x over b by 1. And the second derivative is 0 when the function itself is L over 2. Okay, so let's look at some graphs. Let's say this graph, or any. I need my pencil. Here it is. Okay, so can we identify max min on this? So this is absolute max and local max. And this is local min. This is local min. This is local max because I can show the open interval. All function values are lower and the point exists. So local max. There is no absolute max. This is nothing. And what about this? Yes, but is it a local max or local min? So all function values are smaller, are larger than it. Left and right. All function values are larger than it. So I would consider this a local min. Because if you say, what is local min? I'm going to say is at 1 and it's 3. Are all function values left and right, do they exist? Yes. Are they higher than it? Yes. So the conditions are fulfilled.
So that point right there is a local minimum?
Yes.
Okay.
Because all the point exists. If this were not there at all, I would say there is no local max or local min there. But here, all function values are larger than it. The function exists left and right, and this point exists. So if you ask me, is there a local min? I'll say yes, at 1 and it's 3. All function values left and right are bigger than it.
Okay.
That's the same reason for other. No?
For the this one, yes. Because the function values, so if I don't have this side, then that is not a local max. And it's not an absolute either. But I have, the function exists on both sides. Okay. So the local max value of f is f of c if f of c is greater than or equal to f of x where x is near c. And all function values are greater than that or less than that. So if they're greater than, right, so then c, so f, the number f of c is a local max if all function values near it are smaller, and it's a local max when all function values near it are larger. F of x larger than f of c. Any questions? Okay. What else I was going to? So what about other L'Hopital's rule with, sorry. What about other L'Hopital's rule with functions, with the powers? Yes? Okay, would you like to pick one? Or will I pick one? Yes?
Could you do the how many 7 steps?
Yes, that's the one I'm thinking of, the power one. Yes?
I'm saying, could you identify one?
Yes, yes, of course. Okay, so at the review, I only see one, which is limit as x approaches pi over 2 from the left, from tangent raised to cosine. Is that something you would like to work on? Yes? Okay, let's try. So, 14. on page 352. So this is limit as x approaches pi over 2 from the left from tangent x raised to cosine x. Like with any limit, we have to find the type of limit or the type of indeterminate situation, or maybe the answer is 5 and we're done. So I have to plug it in. So when x approaches pi over 2 from the left, pi over 2 from the left means the first quadrant. Where does tangent go? Yes. Where does cosine go when x approaches pi over 2 in the first quadrant? Yes. So this is one of, I would say, the 3 powers, right? 0 raised to 0, infinity raised to 0, and 1 raised to infinity. Which I think they're the most cumbersome. Okay, our first step is to denote the function. So we will denote the function by y. So then y equals tangent x raised to cosine x. See, that's why we couldn't differentiate this. We have to use log, if you remember. Because there is no differentiation rule for this. So the same thing here, we can't find this limit without applying log to both sides. So this is step number 1. In step number 2, we apply natural log, which now is cosine x times natural log of tangent x. What would be the next step?
1/13.
We have to apply the limit. Yeah, we're not differentiating. So we're applying the limit to both sides. Limit as x approaches pi over 2 from the left from natural log y equals limit as x approaches pi over 2 from the left from cosine x natural log of tangent x. At this point, what is our hope? Our hope is that I can manipulate this function, cosine times the product, cosine times natural log, into a ratio. So if I can manipulate into a ratio and I get 0 over 0 or infinity over infinity, then I'm on straight line, right? There is no more hopes. So let's see. So never bring natural log to the denominator. There will be a catastrophe. So what should I do to cosine? Yes, 1 over cosine, which will turn into secant. Very good. So limit as x approaches pi over 2 from the left, natural log of tangent x over secant x. So I'm hoping now, I don't know yet, I haven't checked, but I'm hoping that this is 0 over 0 or infinity over infinity. So where does the numerator go? Let's think for a moment. We know that tangent goes to infinity when x approaches pi over 2 from the left, the smaller angles. So the first quadrant. Then where does the natural log of infinity go? Yes. So then we have infinity at the top. What about secant? Secant is 1 over cosine. But cosine is 0 at pi over 2. So it would be 1 over 0, which will always go to some sort of infinity. In this case, also positive. So I'm happy now because I see the light at the end of the tunnel by differentiating using L'Hopital's rule because it's infinity over infinity. Do not drop the limit operator, please. So when I differentiate the top, and remember we never differentiate like this a quotient, but inside the limit we are allowed to because we are applying L'Hopital's rule. So when we differentiate the top by itself, we get 1 over tangent times secant squared x. When we differentiate the denominator by itself, which is not allowed unless it's inside the limit, using L'Hopital's rule, we get secant tangent, correct? Okay, I can already get rid of one of them. 1 from the top, a secant from the top with a secant from the denominator, they go away. So now let's see what is left. I have secant at the top. I reverse the tangent because it's tangent over 1. I have to multiply by 1 over tangent. So I have secant x over tangent squared. So this is limit x approaches pi over 2 from the left. So this will be secant x over tangent squared x. On the side, I will make a calculation after I plug it in. So when I plug in pi over 2 at the top, again I get infinity. When I plug in pi over 2 in the denominator, I also get infinity. So it is infinity over infinity. However, let's think for a moment. When we differentiate the top, we get secant tangent. When we differentiate the denominator, we have 2 times tangent times secant squared. Or I look at sine and cosine. So I want to see what's in here with sine and cosine, and then I'll come back. So on scratch paper, if I were to take this test and I have this, on scratch paper I would write this. 1 over cosine x over sine squared over cosine squared. And I have 1 over cosine x times cosine squared over sine squared. I'll simplify one of these. And I'm done, actually, if I do this. And I will. So this continues here. So I have limit. You'll see why in a moment. Pi over 2 from the left. Secant is 1 over cosine x over sine squared over cosine squared. And limit as x approaches pi over 2 from the left. I copy the numerator, which is 1 over cosine x. I flip the denominator. This and this will go away, and now I'm done. I just have to plug it in. No more problems whatsoever. So where is the top going?
0.
Where is the bottom going?
Yes.
However, it's not done. How come it's not done? This is the limit of the natural log. Right. So this was step 3. So I will copy the beginning and I will copy the end. So the beginning says, so this is step 4. I have limit of natural log y when x approaches pi over 2 from the left equals 0. At this stage, in step 5, I swap the operators. Natural log of limit of y when x approaches pi over 2 from the left is 0. And yes, you either come up with the answer or you change it into an exponential equation. E to 0 is this. So limit as x approaches pi over 2 from the left from tangent x raised to cosine x equals e to 0, which is? I went back and replaced y by tangent raised to cosine. I have to. That's the function we had initially. We used the substitution just to make our life easier. Any questions? One thing, last thing that I wanted to review. We've covered everything. Just review, redo all the L'Hopital's rules and everything, all the problems we did in class. But I wanted to look at just one more thing. I just need to find it. Yes. So let's look at this. 32 on 299. So I would like us to answer a few questions here. So we are told that this is the derivative. So this is y equals f prime. This is not the function. So this is the derivative. First question, it's asking us to find on which intervals is f increasing or decreasing. So we know when the derivative, so this is 0. So this is the x-axis. When the derivative is below the x-axis, what happens to the function?
It's increasing.
Right. When the derivative is above the x-axis, what happens to the function?
Increasing.
Increasing. The same thing here, decreasing and increasing. Perfect. So those are the intervals, right? You will say it's decreasing between 0 and 1, union 6 and 8. It's increasing between 1 and 6, union 8 and 9. Agreed? Okay, second question, part B. It says, at what values of x does f have a local max, local min? When the derivative is 0, right? The derivative is 0 in 3 points. From negative to positive. From negative to positive. What is this point? Local minimum. Very good. From positive to negative. And then from negative to positive. Right. So minimum, minimum, maximum. Is that clear? Okay. Next question. At what intervals is f concave upward, concave downward? So let's find where it has inflection points. This is the derivative. You will have inflection points where the derivative has a horizontal tangent, meaning the second derivative is 0. So at this point, at this point, at this point, and at this point, the function, the derivative, has a max min, which means the tangent, second derivative will be 0, right? Okay, so is this a point of inflection?
Yes.
Yes, because increasing and decreasing, right? Is this a point of inflection? Yes, decreasing, increasing, and so on and so forth. But now the question is asking us to find when it's concave upward and when it's concave downward. So, now I recommend the second derivative test, right? So, when the first derivative, if you remember, has a max or a min, then we know that the first derivative is either concave or down or concave up. So let me refresh your memory on that. Assuming there is a critical number here, and the second derivative is positive, what can that critical number be? Minimum. Let's see, there is a critical number here, and the second derivative is negative. What can that be? Okay, so there are basically 3 points, right, where we have max min for this function. At that point, we can determine if it's a maximum, we can determine whether the function is concave up or down. If it's a maximum, it must be concave down. So is this a maximum? No, it's a minimum. So the function must be right between these points. Let's jump to this one. That is a local max. So obviously the function must be concave down. So between these points, the function is concave down. Because right there in the middle is the local max. Does it make sense? I don't think there is anything else. Yes, state the x-coordinates of the points of inflection. They just want us to state the x-coordinates of the points of inflection.
With the 8 going to 9, or
So the points of inflection are when,
yeah, the X. It was on the X, right?
yes, so the points of inflection are when the first derivative has the horizontal
0.
tangent.
Right.
Yes. So at 2, at 3, at 5, at 7.
Can you show me the last concave that you did on the graph?
For this one, when the function has a local max, when the derivative is 0 and it changes sign from positive to negative, then the function has to be concave down.
Okay.
Otherwise, will not have a minimum. I'm sorry. Otherwise, will not have a maximum
And that would be from which point?
between these two.
Between 5 and 7. And
Because
7.
because of the point of inflection.
Okay.
Yes.
And then 7 to 9
Yes.
would be.
Yes,
concave.
because this is a local minimum, so the function has to open upward between 7 and 9.
Okay.
For sure. Because otherwise it will not have a minimum. Are we going to be okay with this test?